In this video, we introduce a question or a couple of questions about the dimension of affine varieties. And we really appeal to our intuition and what we know about solution sets of polynomial equations from prerequisite courses. So remember, last time we defined the term affine variety, and then we looked at some examples. So remember how that worked. First, we have K. K is some field. It has operations of multiplication as well as addition, and basically all of the things that you know about real numbers hold. So multiplication is commutative, so is addition. Multiplication and addition are both associative as well. So you can add and multiply in any order you want, and you can add and multiply in any grouping you want, and both of those are fine. And the distributive property holds. We have both an additive and multiplicative identity, so like a 0 and a 1 in our set, this field K. And we also have a multiplicative inverse and an additive inverse. So that means if you're adding something, there's always something that you can add to it to get that 0 back. Or if you are multiplying two objects, there's always some other member of this field K that you can multiply a particular element of K by so that you get 1, except for the 0 element. So we've got this field K, and we are also thinking about S polynomials, f sub 1 through f sub s, in this polynomial ring. So these are polynomials in n variables, x sub 1 through x sub n. The coefficients lie in that field K that we just talked about. So basically these are just sums or differences of just a scalar from the field K multiplied by x's or different variables x sub 1 through x sub n raised to some power. And those powers are 0 or some positive integer. So it's just like a traditional polynomial. You just have n variables rather than a single variable, and the coefficients aren't necessarily real numbers, but they could be real numbers. They could be any field K, and the real numbers are a field, the rational numbers are a field. Let's see, of course, the complex numbers are a field. So now you have a field and you've got these S polynomials. We can put these two pieces together and talk about the affine variety defined by f sub 1 through f sub s. We denote it this way. And basically all this is the solution set of that set of S polynomial equations in n variables. I guess we could call it the system of S polynomial equations. In n variables, x sub 1 through x sub n. Now, typically we don't write an equal sign in expressions that look like this. We normally write it like this. We're talking about a solution set of this system of equations. And this is a system of equations in n variables x sub 1 through x sub n. So the solution set is going to lie in n-dimensional affine space. So this is a set of points in n-dimensional affine space for that field K that satisfy this. F sub I evaluated at each of those points is equal to 0 for I equals 1 through S. Now, if you're not familiar with this notation, you're probably fine. Most people that would be interested in this video are probably fine and comfortable with this. But just to make this a little bit more concrete for people that are maybe new to this notation, this affine variety defined by the polynomials f sub 1 through f sub s is the solution set of this system of polynomial equations. So you've got f1 of x sub 1 through x sub n equals 0, and f sub 2 of x sub 1 through x sub n equals 0, and f sub 3 of x sub 1 through x sub n equals 0, and so on, and eventually get to f sub s of x sub 1 through x sub n. And you want all of those to be equal to 0 at the same time, and you're just asking yourself, what are the points that I can substitute in here so that all s of these equations are satisfied at the same time? You've done this before. If you have taken a pre-calculus class, you've done this before. If you have taken multivariable calculus, you've done this before, probably with optimization problems involving polynomial functions in 2 variables. We're doing exactly the same thing here. We're just talking about n variables and s equations. We're just making it a little bit more abstract. But this is just the solution of these s equations in n variables. Now, just by definition, as you go from here to here, this is a set of points in n-dimensional affine space. A sub 1 through a sub n are just specific values from that field K. And if we take those points and we substitute them in here, we get 0 for all of them. So I know that affine variety sounds new and it sounds abstract, but it's actually a really simple idea that you're very familiar with and comfortable with. We just never called it an affine variety before. Some of the examples that we looked at in the last video, examples of affine varieties included conics, polynomial functions, rational functions, quadric surfaces, the intersection of surfaces that result in curves, we looked at that twisted cubic last time. That was an example. We had 2 cylindrical surfaces, cylindrical in the multivariable calculus sense. And those 2 intersect in this twisted cubic function. So here's the question for this video. We might be interested in answering this. We might ask ourselves, what's the relationship between the number of equations that we're starting with, the number of variables those equations are dependent upon, so x sub 1 through x sub n, and the dimension of the affine variety, f sub 1 through f sub s. Now, just to give you an intuitive sense of dimension, let's look at some examples. I'm not going to define dimension formally here. It would be helpful to take linear algebra to get your first definition of dimension. But I think we all know that sets of points are zero-dimensional objects, and curves are one-dimensional objects, and surfaces are two-dimensional objects, and so on. So here's a relationship that you might notice. Okay, so let's say we have one equation. We're trying to look for this relationship between the number of equations, the number of variables, and the dimension of the resulting affine variety. Well, if we have one equation and our affine variety, and maybe we have two variables, our affine variety would look something like this. We have the affine variety is some function f of xy, or is defined by some polynomial f of xy. So this is going to be the set. This is by definition the set of all points in two-dimensional space. And let's just use the real numbers for our field here, such that f of xy equals 0. Well, generally what you're going to get from this is a curve. So this has dimension 1. So we would write it this way: the dimension of V is equal to 1, and the result is a curve. Or perhaps several curves if you're talking about something like a rational function. So we looked at examples like this last time. If we have v of y minus x squared here, that's a set of all points in the xy plane such that y minus x squared is equal to 0. And if we add x squared to both sides, we get y equals x squared. So I've got a function of two variables here, a polynomial in two variables, and that leads to a one-dimensional object. Okay. Let's look at more examples. Okay, let's keep the number of equations the same, but then raise the number of variables. What if we have 3 variables? Well, in that case, our variety is defined by a single polynomial function in x, y, and z. This is going to be a subset of three-dimensional space. And it's a solution set of this equation. If you've taken Calculus 3, hopefully you see this and you think of that as a surface. There might be some regions over which we could solve this for z or x or y as a function of the other two variables. So we can think of this as the implicit definition of those functions of x, y, and z respectively as we change our perspective and look at each of them as the dependent variable. But generally, this is a surface. And a surface is two-dimensional. So we had one equation, we had 3 variables, and the dimension was 2. Over here, we had one equation, we had 2 variables, and the dimension was 1. So it looks like when we have one equation, if we have 2 variables, the dimension is 1 less than that. If we have 3 variables, the dimension is 1 less than that. And let me give you a concrete example of this. Let's say you've got v of z minus x squared minus y squared. Well, that's the set of all points in three-dimensional space. We're going to use the real numbers as our field again. such that z minus x squared minus y squared is equal to 0. And if you've taken calculus 3, you know that that's just an elliptic paraboloid. I guess it's kind of a circular paraboloid, isn't it? And that's a surface. It's a two-dimensional object that lives in three-dimensional space. And it's sort of easy to see that it's a two-dimensional object because we think of x and y varying, and then that's giving us a particular z value. So as x and y vary, we get a single z, and that means it's two-dimensional. Over here, when I had this function of two variables, I was able to solve it for y, and now I have y as a function of one variable. So it's like we're using one of the variables as the dependent variable. We're using all the other variables as independent variables. And when we do that, the dimension of v comes from the number of independent variables you see over here. So since this depends only on x, since this function y depends only on x, we get a curve. Since this function z depends on two variables, x and y, we get a surface. Now we also saw that if we change this up a little bit, let's increase that number of equations to 2. If we have 2 equations, and those equations are in 3 variables, now our variety consists of setting 2 surfaces, or setting 2 polynomial functions in x, y, and z equal to 0. So this is still a subset of three-dimensional space because these are functions of 3 variables. Now I want f to equal 0 and g to equal 0. And since I have f and g both equal to 0, I've got one surface here and another surface here. And now we're going to look for where those surfaces intersect, kind of like our twisted cubic. So the resulting object, that variety, isn't a surface like it was up here. This is an intersection of 2 surfaces, and then somehow, because we have an intersection of 2 surfaces, generally we get a curve. Which is a one-dimensional object. You can imagine tracing that out, letting one variable, let's say time, for example, letting t vary, and then you can trace that out. Now, as t varies, you're able to trace out the whole curve. So that's 1D. So it looks like we took this number of variables, and if we have one equation and we have 3 variables, the result, the dimension goes to 2. So we subtracted 1 for that equation. When we had one equation and 2 variables, the dimension went down by 1 as well. The dimension we're starting in, or we're in a subset of two-dimensional affine space, and the dimension is 1 less than that dimension of the space that we're talking about. So this is two-dimensional affine space. 1 less than that is a one-dimensional object, which is a curve. Here we're in three-dimensional affine space. We're thinking of that as all of R3 in this case. And when we graph something like that, we end up with a surface, just like this example here. Now here, we're talking about 2 surfaces, and where they intersect, generally that's going to give us a curve, which is a one-dimensional object. So we might think, okay, if I have 2 equations with 3 unknowns, well then each of those equations is providing a constraint, and so the dimension goes down by 1 every time. So every additional equation should reduce the dimensionality by 1. So let's say we've got 3 equations and 3 unknowns. So this would be a subset of three-dimensional space. We want f, g, and h to all be 0. Well, you might think this is a zero-dimensional object. Your intuition probably tells you that if you have 3 equations and 3 unknowns, you're going to be looking for a set of points. And sets of points are zero-dimensional objects. Now, that's just our intuition. When I say that this is this set of points and this is this, and that this always gives us this, that is, there really should be a question mark there. Question is that always true? Is it true that every time we have a set of 3 equations and 3 unknowns, we always get a set of points? And is it true that if we always have a set of 2 equations with 3 unknowns, the result is a curve? And is it true that if we have 1 equation with 3 unknowns, we always get a surface? I think we know that that's not true. Let's think about it. Just in a pre-calculus sense, if you have 2 equations and 2 unknowns, so your variety is defined by 2 polynomial functions of 2 variables. So this is a set of all points x, y in 2-dimensional affine space where we're choosing our field to be the field of real numbers just to help our intuition. And we want f and g to be equal to 0 at the same time. Well, you know that if you have 2 equations and 2 unknowns, let's say that those are linear equations, it's possible that you get 1 point of intersection. If we have 2 linear equations and 2 unknowns, you might have a single solution. That's a possibility. Single point of intersection of those 2 lines. So in that case, the variety consists of a single point, which is a zero-dimensional object, or you might have no solutions. Maybe the 2 lines are parallel to each other. So we can't even talk about the dimensionality of the empty set. We would call this system an inconsistent system because there's no way that f can equal 0 and g can equal 0 at the same time. Or it's possible that f and g are actually the same line. You know this pre-calculus stuff. And it might just be the set of all points x, y in 2-dimensional space such that f is equal to 0, which is the same as g equaling 0. And that's 1-dimensional. So we might think that if we have 2 equations and 2 unknowns, well, the number or the dimensionality of the solution set should just come from subtracting those. I've got 2 variables, and then I get 1 constraint for each of the equations. So with 2 equations and 2 unknowns, I would expect to have a 0-dimensional object. But sometimes we don't get a 0-dimensional object. Sometimes we get a 1-dimensional object. And sometimes we get an inconsistent system. So we don't get any solutions at all. We call that the empty set. The same is true for 3 dimensions. Let's still stay with that case of 3 linear equations and 3 unknowns. Well, the possibilities there are these. Let's say you have ax plus by plus cz equals d, ex plus fy plus gz equals h, ix plus jy. I'm sorry for using I and j in this way. And f and g, just kz equals L. I know we don't usually use those variables or those coefficients or those letters for those roles, but that's okay. So you've got 3 equations and 3 unknowns. Each one of those is a plane. Well, it's possible that you could have a plane there and another plane over here, sort of intersecting at an angle. And maybe this is plane 1, this is plane 1, this is plane 2, and this is plane 3. Maybe plane 1 and plane 2 are the same. And then this is plane 3, it's a different plane. Well, then you don't get a single solution, you get a one-dimensional solution, because the solution of this system of equations is a curve. If you've ever taken pre-calculus or taught pre-calculus, you know most of the problems that we pose in that class involve 3 planes intersecting each other. So we'd have this plane and then another plane, and we'd say, oh, they only intersect at a single point, and we try to find that point. But it's possible that they intersect along a curve. It's possible that they don't intersect at all. Maybe you've got 3 parallel planes. So that's another case where the affine variety would be empty. But yeah, the fact that we have 3 equations and 3 unknowns doesn't necessarily mean that we're going to have a 0-dimensional object, but our intuition might suggest that that's what happens, because our intuition suggests that, okay, if I've got 2 variables here and I only have one equation with 2 variables is going to give me a curve, and one equation with 3 variables is going to give me a surface. And one equation with 4 variables is a little bit harder to think about, but we could, I guess, solve that for W in terms of X, Y, and Z, and that would at least be defined on a solid region in 3-dimensional space. But we see, as we stick with dimensions that are comfortable for us, like a 0-dimensional, 1-dimensional, 2-dimensional, and up to 3-dimensional, we see that as we add more equations, we tend to lose a dimension in the solution set. If I've got a surface here and a surface here, when the 2 surfaces intersect, I get a curve. Or if I have a surface and a surface and a surface, like those 3 planes that I was talking about, I might get a single point. Or if I have a line and a line, or a function of 2 variables and a function of 2 variables in general, maybe you just have a parabola and a line. You could get 2 solutions. So that would be a 0-dimensional object, because a set of points is 0-dimensional, with 2 equations and 2 unknowns. If the 2 equations are just multiples of each other, you would get a curve. And if the equations cannot both be satisfied at the same time, if maybe you're talking about this parabola and this line, they don't intersect at all, well, then you have the empty set as your solution. So when we ask ourselves, what's the relationship between the number of equations, the number of variables, and the dimension of V, it's not simple, but there's something about this pattern that if I have 1 equation and 2 variables, the dimension is 1 less than that. And there's 1 equation and 3 variables, the dimension is 1 less than that. If I have 1 equation and n variables, I would expect the dimension to be n minus 1. But as I add more equations, we would say typically I would expect each equation to reduce the dimension of the affine variety by 1. So if I've got 3 variables here, I've got 2 equations and 3 variables, I would expect the dimension to be 1. 3 equations and 3 variables, I would expect the dimension to be 0. 2 equations and 2 variables, I would expect the dimension to be 0. But we know from some very simple examples that we studied in pre-calculus and college algebra, I mean, easy stuff, linear algebra stuff, really, that's not always the case. And if we're not able to just subtract, the question is, when can we just subtract? When does that work? Because most of the time, if you have 2 equations and 2 unknowns, you think, I should be able to solve it most of the time, unless it's a very special case, one of these 2 special cases, or this special case, or the special case where you just have the same curve twice, like we have right here. So let's look at some more examples and then talk about that intuition. Let me put that in writing for you. Our intuition suggests that since each equation will impose an extra constraint, every additional equation should drop the dimensionality or the dimension of V by 1. So if we have n equations or m equations with n unknowns, our intuition suggests that the dimension of V should be n minus m. So when I have one equation, the degree is 1 less. When I have 2 equations, the degree is 2 less than the number of unknowns. When I have 3 equations, the degree is 3 less than the number of unknowns, and so on. But this isn't always true, as we've seen over here. We expect 0 dimensions when we have 2 equations and 2 unknowns, or 3 equations and 3 unknowns. But we know that there are some special times when we don't, when this doesn't quite work. There's something about this that doesn't work, but sometimes it works. And we know sometimes it works in the problems that we tend to pose in a pre-calculus class. Let's look at some non-pre-calculus examples. So this is an example from that Ideals, Varieties, and Algorithms book by Cox, Little, and O'Shea. So let's say we're interested in this variety. It's defined by 2 simple polynomial equations and 3 variables. So the solution set, should be a subset of 3-dimensional space. And remember what this means. Oops. Well, this is fine. This is defined to be the set of all points x, y, and z in 3-dimensional space, such that x times z equals 0 and x times y equals 0. Now, I actually wrote the problem down wrong, so this is not identical to the problem in the book, but the principle is the same. I just changed a couple of the variables. So you might ask yourself, in 3-dimensional space, what does that solution set look like? Well, let's look at the equations. You've got x times z equals 0 and x times y equals 0. Well, the only way the first one equals 0 is if x equals 0 or z equals 0. So this first equation leads to this fact. We're going to separate the solution set into 2 cases. In one case, x is equal to 0. In the second case, z is equal to 0. Now we also need, you've got to have this case or this case. Now one of those cases to be true for the first equation to be 0. Now we also need x times y to equal 0. But if x equals 0, x times y already equals 0, so case 1 is done. If x is equal to 0, both of these are satisfied. But if z is equal to 0, and we're assuming for right now that x is non-zero, well, then the only way that this equation could be satisfied and this equation can be satisfied if x is not equal to 0 is if y is also equal to 0. Now, x equals 0 is a plane. X equals 1 is sort of close to us. It's a plane that's 1 unit from the YZ plane back here. x equals -1 is 1 unit behind that, but the YZ plane itself, like that's the x equals 0 plane back here. Oops, x equals 0. Now here we're saying that z has to be 0 and y has to be 0, but x is free to be anything. So if x is free to take on any value, and z and y are both forced to be 0, we must be talking about the x-axis, because z is equal to 0 on the x-axis, y is equal to 0 on the x-axis. So the affine variety given by these two equations consists of two parts. It consists of a plane, the YZ plane, and this line that goes through it. It actually probably would have been better to use the example that they gave us. Let me show you the alternate example. They have z, or the variety defined by xz equals 0 and xz and yz, sorry. So we set both of those equal to 0. And then we look at the solution set of that system of 2 equations and 3 unknowns. Since we have 2 equations and 3 unknowns, we would expect to take this 3-dimensional affine space and then just reduce by 2 to get an object that would just be 1-dimensional like this. But we don't get a 1-dimensional object. We get a 1-dimensional object and a 2-dimensional object at the same time. So V is actually composed of 2 pieces, the entire x-axis here and the entire plane x equals 0. On this one, when we have xz equals 0 and yz equals 0, well, there are 2 ways that those products can be 0. Either z is equal to 0, or x and y are both 0 and z is free to be anything. Now, x or z equals 0 is the yz, or the xy plane, excuse me. And this is the z-axis. It's a little bit harder to draw with the x-axis or the x variable playing that role. So I'm going to draw it with the z variable playing that role. But z equals 0 is just down here. It's like the floor. Z equals 1 is 1 level up. Z equals 2 is 2 levels up, and so on. And y and x are both 0 on the z-axis. So this affine variety consists of 2 pieces. We had 2 equations with 3 unknowns. And we might expect the object to be 1-dimensional. And it does have a 1-dimensional piece, but it also has this 2-dimensional piece. So we see, again, that this doesn't always work. Now, going back to that linear algebra example, if you've taken linear algebra, you've probably seen the systems of linear equations and n unknowns. So let's say we have m linear equations in n unknowns, x sub 1 through x sub n. So the first equation we'll call a sub 1, 1 times x1 plus a sub 1, 2 times x2 plus a sub 1, 3 times x sub 3. The first number here denotes which equation you're on. It's the first equation. And then the next one will have a sub 2, 1 times x1 plus a sub 2, 2 times x2, a sub 2, 3 times x3. And eventually we have m equations, not n equations, but m equations. So you might expect that the dimension of V is equal to n minus m. Just like we expected up here that if we have m equations and n unknowns, the dimension would be n minus m. But that's not the case. And hopefully you remember from linear algebra that it really doesn't depend on the number of equations, it depends on the number of independent equations. Oops, independent equations, and I've run out of space. Kind of like we were talking about here with our pre-calculus examples. These two equations were just multiples of each other, or potentially exactly the same equation, or these two polynomial functions that we're setting equal to 0. When we set those equal to 0 and rearrange them, those two equations were equivalent to each other. And so we just ended up with the same equation twice. The same would be true over here. If I had a parabola and then the same parabola for both of those equations, the result does not have dimension 0. The result has dimension 1. The solution set of two equations and two unknowns, if one of those equations is just another version of the first equation, we don't get just a set of points. We get infinitely many solutions that lie along a curve. The same is true here. If we have 3 equations and 3 unknowns and they're all independent from each other, we get a single solution. X naught, Y naught, Z naught if you prefer. But if you've got 2 of these equations that are dependent on each other, so equation 1 and equation 2 are basically the same equation, just sort of manipulated so that when you graph them, you have exactly the same plane. Well, we only have 2 independent equations here, and then the result is one-dimensional. Or if you have 3 equations that don't have anything in common, except for maybe that they all represent parallel planes, there's no way for all 3 of them to be satisfied at the same time. So the solution set of that system of 3 equations and 3 unknowns is the empty set. So the dimension here for m linear equations and n unknowns isn't n minus m unless those are m independent linear equations. But if any of them are dependent, we're not going to get this. We know from linear algebra that the number of independent equations is related to the rank of the corresponding coefficient matrix for this guy right here. So it turns out that in this case, the dimension of V is equal to the number of variables that you started with minus the rank of that matrix, the coefficient matrix over here. So again, it is related to this idea of independent equations. And we talked about that in linear algebra. But we're going to do exactly the same thing here. There's something about these 2 equations that makes them not independent of each other. We can't just subtract the 3 unknowns minus the 2 equations and say, okay, we should get a one-dimensional object. Because we do get a one-dimensional object sometimes. We also get a 2-dimensional object sometimes. So this notion of independence is an important notion. It's slightly different when we're talking about affine varieties, which are defined by polynomials. And those polynomials correspond to polynomial equations, systems of polynomial equations. And the affine variety is just the solution set of that system. We need to have some sense of what it means for 2 polynomial equations to be independent in order to be able to talk about the dimension of an affine variety B. So I guess the whole point of this discussion is to say that our intuition is sometimes wrong. This is something that we know to be true sometimes. We know that each equation should apply, or it should impose an additional constraint, and then the dimension should drop by 1. But I guess we should say, under certain conditions, that works. And we haven't really discussed what those conditions are, but we've talked about the fact that we've seen this before. Most of the time we can subtract 2 equations and 2 unknowns has 1 solution. 3 equations and 3 unknowns will have a finite number of solutions. 2 equations and 2 unknowns will have a finite number of solutions. And if it has a finite number of solutions, that's just a set of points. That's 0 dimensional. You just subtract 2 minus 2 and you get 0 dimensional objects. But not always. And that not always part relates to, or is related to, the dependence or independence of these polynomial functions that define the affine variety that we're interested in. Now, I didn't pose this as an affine variety, but obviously you could take each of these constants, d, h, and l, subtract those constants from both sides, and then you would have these set equal to 0. And so the affine variety that's associated with this system of 3 equations and 3 unknowns is the affine variety defined by the polynomials given by this minus d and this minus h and this minus l. So we might get 1 solution, or if they're not linear equations, we might get a finite number of solutions. You've probably done that before in Calculus 3 if you've taken Calculus 3, but sometimes we have an infinite number of solutions, sometimes we have no solutions, sometimes maybe they're all the same plane, and so we end up with something that's a 2-dimensional object. So the dimensionality is not just this, but it has something, this number that we end up subtracting has something to do with the number of independent equations. And then we're going to say, well, what does it mean to be independent when you're talking about polynomial equations and affine varieties? That will be discussed later. So that's the end of this video. We really didn't answer the questions, but we talked about some interesting questions about the dimension of affine varieties. Hopefully that got your got your curiosity piqued, so that you can think about how we might answer those questions later and what it might mean for polynomial functions to be independent from each other. In the next video, we're going to talk about finite unions and intersections of affine varieties, and then we'll look at a pretty simple application of affine varieties to robotics with a particular robot arm.